In this video, we'll finish off exercise 721, where we're trying to draw the full, complete mechanism of an Sn1 reaction. And the first step, as we've been seeing, is to figure out which of these curved arrow patterns we'll be using. These are all the possible things that could happen in an Sn1 reaction. Well, let's think about this proton transfer at the beginning. You only need that if you have a bad leaving group. But we have a great leaving group. Bromine, like all of the halogens, is really big, so it can take those electrons and spread it out over its enormous space, and that helps to dilute the charge and to stabilize it. So it's a great leaving group. So we don't have to do this first proton transfer. In every substitution reaction, you'll always have to do loss of a leaving group. Let's think about carbocation rearrangement. Imagine drawing the leaving group off the molecule. It leaves, takes the electrons away. And so now you would have a positive charge on that carbon. Well, that is a tertiary carbocation because it's bonded to 1, 2, 3 other carbons. Next door, you either have a primary, another primary, or a tertiary, 1, 2, 3. So no position next door is more stable than the position that the carbocation is already in. So there's no incentive to move, and there's no carbocation rearrangement. So we don't have to worry about the carbocation rearrangement here. We won't have one. And just to confirm that, the nucleophile, you can see, adds at the same position as the leaving group. So if it's on the same position, then the carbocation must not have rearranged. In every substitution reaction, you'll always have nucleophilic attack. And finally, for the proton transfer, we're only going to have this proton transfer at the end if the nucleophile has no charge. If we look at our nucleophile, we notice that we have a metal and nonmetals, so that's really an ionic compound. That's a sodium with a full positive charge and an SH with a full negative charge. The sodium is really big. It's all the way on the left on the periodic table. Atoms get bigger as you go to the left and as you go down. And so it's going to stabilize and dilute that positive charge and go off and gallivanting, living its best life. In the meanwhile, this SH minus, that's going to be our nucleophile. And that has a full negative charge. We only have to do this proton transfer at the end if the nucleophile has no charge. Because the nucleophile has a full negative charge, we don't have to do that. So this is about the simplest Sn1 mechanism that you could do. You only have loss of a leaving group and nucleophilic attack. Okay, so we can start by drawing our beautiful molecule here with our bromine, and our first step will be loss of a leaving group. Our leaving group is bromine, takes its electrons, picks them up, goes out of town. So we have a full positive charge where the bromine was. And now we have that bromine with a full negative charge floating around somewhere in the beaker. The next step, because we don't have that carbocation rearrangement, the next step is nucleophilic attack. So that's what we're going to show here. We have our awesome electrophile already with a full positive charge. We just need to add our nucleophile, and as we saw earlier, our nucleophile is going to be this SH minus. So that has that full negative charge. It has a whole bunch of lone pairs, so it's an awesome nucleophile, and it attacks the electrophilic carbon. So there's our nucleophilic attack. And finally, we have our product. And that is that. That's the product that we were hoping to get. So that's the mechanism for this whole thing. We first looked at which of these steps we needed to include. We made sure we included them. We had loss of a leaving group and nucleophilic attack, just the standard staple bread and butter Sn1 reaction. So the last one for this exercise is H, the last example of drawing a complete Sn1 mechanism. So here, let's see, we're going to see which one of these different steps we need to include. We only have to do this proton transfer at the beginning if you have a bad leaving group. Well, what is our leaving group? bromine. Bromine is an amazing leaving group. It can take those electrons, spread them out over its enormous size, and stabilize them by diluting them in space, by diluting that charge. So we have a great leaving group. You only have to do this if you have a bad leaving group, so we don't need to do that proton transfer in the beginning of the mechanism. You'll always have to do loss of a leaving group in a substitution reaction. If you were thinking of the carbocation rearrangement, imagine the leaving group comes off, you have your carbocation there. This is a tertiary carbocation. Each of the positions next door is, or none of the positions next door is more stable. At most it's just as stable, but that doesn't leave any incentive to move, and so you don't get any carbocation rearrangement there. And a confirmation of that is that the nucleophile adds at the same place. So that implies that the carbocation didn't rearrange. You always have nucleophilic attack in a substitution reaction. And for proton transfer, we just have to think about what our nucleophile is. Remember, the ET is an ethyl group, so that's CH3CH2, and we have an OH on the end. These are all nonmetals, so this is a completely covalent compound. There's no full negative charge. Well, when there's no full negative charge on the nucleophile, you have this proton transfer, so we will draw that in. So our Sn1 mechanism is going to have 3 steps. So let's draw that first molecule. First step is loss of the leaving group. Our leaving group is bromine, so it takes those electrons and gets out of town. It leaves behind a carbocation. And your bromine has that negative charge floating around the solution somewhere. The next step that we have is nucleophilic attack. So our nucleophile is ethanol, drinking alcohol. So I'm going to draw that down here. That oxygen is really electronegative, so it pulls electrons to itself. The carbon that it's bonded to and the hydrogen are both slightly positive. Also note that the oxygen has 2 lone pairs. So the oxygen is very clearly our nucleophile, and that attacks the full positive charge in the electrophile, the carbocation. So there's our nucleophilic attack. And let's just add a little more space here. Oops. Okay, so once you get that nucleophilic attack, you have that with a full positive charge on the oxygen, and it's to get rid of that charge that we have to do this last step, the proton transfer, at the end. So to do that, you can use anything that has a lone pair or a slightly negative charge or full negative charge in the solution. Just for the sake of simplicity, I'm going to use this bromine, but the truth is it would probably be another ethanol molecule. But okay, this has a negative charge, steals the hydrogen and the electrons that were bonding the hydrogen to the molecule. Those go to the oxygen to help to stabilize that positive charge. So we end up with that molecule there. And that is actually the same thing that they wanted us to get. Now note, they will probably use an ET for that ethyl group, but that's just a naming convention. Otherwise, the molecule is exactly the same. And so this was our mechanism, and this was our last complete mechanism to draw for an Sn1 reaction in the homework. So remember, the full process for doing this is to write out this flowchart, consider one by one which of these steps you need to include, and then to draw them very carefully and clearly. Okay, so that concludes